Okay, the topic that we're going to introduce today is something, we're going to go back to complex numbers, and we're going to talk about, we're going to develop ways to find the powers and the roots of them. Now, we're not going to get to that today, but we are going to kind of uh, talk about complex numbers again, talk about complex numbers in terms of polar coordinates, and talk about something called the complex plane. Now, we've already talked about rectangular coordinates and polar coordinates, but now we're going to talk about the complex plane. Now, a complex number, we can represent it by a real part and an imaginary part. So, for example, we're going to call the complex number Z. In this book, or usually in math, complex numbers are designated by Z. It's equal to x plus yi. Now, this part is the real, and this is the imaginary. Now, the way we graph this, we're going to create something called the complex plane, and the complex plane looks exactly like an xy coordinate system, but the x-axis is our real axis, and then the y-axis is our imaginary axis. Okay. That's not supposed to say x real axis. This is the x-axis, which we designate the real axis. It's not something called x real or something like that. Okay? This is the real axis. That's the imaginary axis. They just correspond to x and y. So, for example, if I want to graph the complex number z is equal to root 3 plus I, here my real part is root 3, which is around 1.7. And then my imaginary part is a 1, because there's no number there. So it is going to be graphed somewhere around 1.71. Okay? And that point is z is equal to root 3 plus I. Okay? And so something like, I could graph the point. This would be, for example, z is equal to negative 2 minus I. Negative 2 on the x-axis because that's a real part. And then I go down 1 because my I has a coefficient of negative 1. So that's negative 2 minus I. Now, the next part is we're going to talk about some terminology when we're dealing with complex numbers that we haven't really been introduced to before. So the first thing is the magnitude or modulus of Z. Now it's denoted by this absolute value of Z, and it really represents the distance from the origin to your point in the complex plane. So this is kind of how what the modulus really is. And you've actually seen this many times already. If this is imaginary and that's real, and this is a complex number, the modulus is the distance from the origin to your point. So this is denoted by the absolute value of Z. Now, since we graph complex numbers on the complex plane, which followed the rectangular system, I know I can find this distance by doing the square root of x squared plus y squared. Just like how in the polar coordinate system, r was equal to the square root of x squared plus y squared, the same thing here, the distance from the origin to the point is also the square root of x squared plus y squared. And so that's the definition for the modulus or the magnitude. And then now the definition of the modulus of z is consistent with the definition of the absolute value of a real number. So for example, if z is equal to x plus yi, if z is real, then z is equal to x plus 0 times I, because there's no imaginary part. And so if I want to find the magnitude of this z, it would be the square root of x squared plus 0 squared and this is the square root of x squared, and the square root of x squared is really the absolute value of x. And so that's why we use this notation when we talk about the magnitude of z, this absolute value notation, because it corresponds to the absolute value in real numbers. One last thing we're going to talk about here is the magnitude of z in terms of the conjugate. So remember that if I have a complex number z, its conjugate which we'll call z bar, okay, is really x minus yi Now, what happens when we multiply a complex number with its conjugate? Well, remember that this is, if I have z times z bar, this is really x plus yi times x minus yi. And this is really x squared. The two middle terms cancel out, and I'm left with negative y squared I squared. I squared is negative 1, so this is really x squared plus y squared. Okay. So if you take note at what the magnitude of z is the square root of this, and if I have z times its conjugate is equal to x squared plus y squared, then this tells me that the magnitude of z is equal to the square root of a complex number times its conjugate. Okay, so that's all the theory behind of what we're going to learn today. You're not going to be tested on stuff like this, but it kind of helps us form the discussion of the problems that we're going to do today. So let's go ahead and move to the back, or if you need more time, you could take some time or pause the video. But here's what we've talked about so far. You could map complex numbers on a complex plane. The magnitude of z is the distance from the origin to the complex number, and it's just the square root of x squared plus y squared. And then we talk about multiplying the complex number by its conjugate, and the distance is the same thing as multiplying the complex number and the conjugate and taking the square root. Okay. Now, we're going to talk about converting a complex number between rectangular form and polar form. Since we are in the chapter of polar coordinates, and we've been doing this for the past couple of lessons, we're going to talk about switching from rectangular form to polar form. Now, remember, to switch to polar, kind of the formula to get from polar to rectangular is x is equal to r cosine theta and y is equal to r sine theta. If z is equal to x plus yi, we just replace x and y with what the polar form. So this is equal to r cosine theta plus r sine theta times I. Okay? So this, what we just wrote here, is the polar form of a complex number. Now, the way it's usually written is not in this way, because this way is kind of like confusing a bit. The way they write this is z, the complex number. What they do is they factor out the r, and so it looks like this. This is what you're really going to need to know for this lesson. This is the polar form of a complex number. Z is equal to r times cosine theta plus I sine theta. Okay. This also is another important thing. If z is the complex number in polar form, the angle is called the argument of z. Now, make note of this. The angle has to be between 0 and 2 pi. Okay. And that will come into play a little later when we do some of our problems. So, it's called the argument of z. Also, because r is greater than or equal to 0, we have r is equal to this. And this is actually something I was talking about on the front page. If r is equal to this, and we talked about in the very beginning that that's the same thing as the magnitude of z, the magnitude of z, which is the distance from the origin to the complex number, is the same thing as r, which is the distance in polar coordinates. Okay, now we get to actually do some problems. So example 1 says we want to plot this number in the complex plane, and then we want to write the number in polar form. So if we're going to plot this in the complex plane, I think I actually did it. Oh no, it's root 3 plus I. So if I want to do root 3 minus I, root 3 is around 1.7, and minus 1 is here. So this is z is equal to root 3 minus I. Now, if we want to write this number in polar form, I know it's in quadrant 4. So if I want to write it in polar form, I need my r and I need my angle. Well, r is pretty easy. It's the magnitude of z, right? So r is equal to the square root of x squared plus y squared. And so this is equal to the square root of root 3 squared plus negative 1 squared so this equals to the square root of 3 plus 1, which is just 2. Okay. Now, if r is 2, x is root 3, and y is negative 1, what I'm going to do to find my angle is I'm going to write my sine and my cosine. So if this is r, then I know sine theta is equal to y over r. Y is negative 1, so that's negative 1 over 2. And then cosine theta is equal to x over r. So that's root 3 over 2. So now you ask yourself, what angle has a sine of negative 1/2 and cosine of root 3 over 2? Well, I know my sine 1/2 is a 30-degree angle, but if my cosine is going to be positive and my sine is going to be negative, then I'm in quadrant 4. The quadrant 4 30-degree angle is 11 pi over 6. And then the final thing that they want me to do is write the number in polar form. So up here is the number in polar form. I just copy what it says and I just replace it with the r and the theta. So my complex number in polar form is 2 because that's my r, cosine 11 pi over 6 plus I sine of 11 pi over 6. And this is my complex number. Yeah. So that rectangular coordinate is that in the polar coordinates. Okay, so there's a DIY for you to do on your own. So please pause the video to let the students work. And then when they're done, you could go ahead and turn it back on or play. So in this example for the DIY, you're going to plot this point in the complex plane. Really simple. It's just 1, 1. Okay, so this is z is equal to 1 plus I. Now I'm going to find my r. R is equal to the square root of 1 squared plus 1 squared. So that's equal to the square root of 2. And then I know that sine theta is equal to y over r, which is 1 over root 2. I rationalize this, and I get that this is root 2 over 2. And my cosine theta is also 1 over root 2, so it's root 2 over 2. Well, that's pretty easy. Which is my angle that has a sine and cosine of root 2 over 2? It's pi over 4. So theta has to equal pi over 4. And so now I have my r and I have my theta. So z is equal to root 2 cosine pi over 4 plus I sine pi over 4. Okay, so take some time to jot that down, and then we'll move on. Okay, now let's look at example 2. Now I'm going to go the other direction. I'm going to start with polar polar coordinates and I want to go to rectangular coordinates. So they asked me that I need to plot this I'm going to plot it in the complex plane and write an expression in the rectangular form. Now, if this is my polar form, I know r is 2. And my angle is 30. Right? This is r and that's theta. So on the in polar form, this complex number corresponds to 30 degrees, and that's really easy to graph. Now it's okay if it says to plot it on the complex plane. We just still do the real, and we do the imaginary. And what I do is I still go ahead and just graph 30 degrees. This is around right here. And then I'm going to go ahead and mark 2 here. So 2 cosine 30 plus I sine 30, that's my r, that's my theta. So that's that angle. Sorry, that's the point on the complex plane. We just use the polar form to graph it. Now we want to write this in rectangular form. Now, actually, I think this way is much easier. If I have 2 cosine 30 degrees plus I sine 30 degrees, all I do is I just evaluate what the cosine of 30 and the sine of 30 are. So z is equal to 2. The cosine of 30 is root 3 over 2. And then sine 30 times I. Sine 30 is just 1/2. And all I do is I just distribute. So if I multiply this in, the 2's cancel. So z is equal to root 3 plus I. Pretty straightforward. Okay, now look at the DIY. Go ahead, pause the video now so they can work on the DIY on their own, and when they're done, you could play it so they could check their answer. Okay, so in this DIY, it doesn't tell you to graph it, so we're not going to graph it. I just wanted to switch this to rectangular form. So z is equal to 2 cosine of 120. 120 is the 60-degree angle in quadrant 2. So if I'm at 60, my cosine is 1/2. But since I'm in quadrant 2, this should be negative 1/2. The sine of 120 is root 3 over 2. Oops. And I just go ahead and distribute. So z should be equal to negative 1 plus root 3 I. Okay, now we're going to talk about the... So we know how to multiply complex numbers if they're rectangular coordinates. It's really just a form of binomial multiplication. However, if they are in polar form, there is a different way to go about multiplying the complex numbers. Okay? So the multiplication, so let's say z, let's say I have a complex number and it's, I call it z1, so it's r1 cosine theta 1 plus I sine theta 1. And I have a second complex number, we'll call it z2, and it's r2 cosine theta 2 plus I sine theta 2. If I, this is the rule for multiplying them. If I multiply z1 times z2, or if I multiply two complex numbers together, what you really do is you multiply the r's together. So it's r1 times r2. And then you multiply that by the cosine of the angles added together plus I sine. Okay, so there it is. Z1, Z2 is equal to the distances multiplied together. Cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Now, if you are going to divide them, so this is the multiplication. The division, if it's Z1 over Z2, it's actually going to be, instead of multiplying these, it's going to be R1 over R2. And this is going to be the same thing, except instead of addition, it's subtraction. Okay. So write those down, and then we'll move on to actually using these to solve problems. Okay. So here I have two complex numbers. Z is equal to 3 times cosine 20 plus I sine 20. And I have W is equal to 5 cosine 100 plus I sine 100. And I want to multiply them and I want to divide them. So let's multiply them. If I do letter A and I multiply them, Z times W is really just 3 times 5. And then it is the cosine of 20 plus 100 plus I sine of 20 plus 100. Okay. Now, for most of you, you could probably skip that step, but that's just the substitution. If you look on the previous page, that's the formula. And then so what you do here is you just work it out. Z times W is 15 cosine 120 plus I sine of 120. And that's it. Don't evaluate this because they want it in polar form. If don't find the cosine of 120 or find the sine of 120. If they ask you to change it into rectangular form, then yes, you could go ahead and do that. But right now, this is the answer in polar form. That's letter A. Now letter B. If I want to divide Z by W, I get 3 over 5 cosine of 20 minus 100 plus I sine of 20 minus 100. And so this turns into 3/5 cosine of negative 80 plus I sine of negative 80. Now, This would be fine, but this is where the thing from the first page kind of shows up again. That if we have a complex number, we want the argument of z to be between 0 and 2 pi. So what I have to do is I have to add one revolution so that I'm between 0 and 2 pi. So this is really 3/5 cosine of 280, because I just added 360, plus I sine of 280. And that is the quotient of the two complex numbers. Okay? So now you know how to multiply and divide complex numbers in polar form. Okay, and that's it for the lesson. Oh no, I'll pause the video and do the DIY on your own. Sorry about that. Okay, so this one is actually much easier than the one on top because I don't think there's a conversion here. So ZW is equal to, just check your answers here. 2 times 4 is 8. Cosine of 40 plus 20 is cosine 60 plus I sine 60. And if I do the division, Z over W is equal to, I think it ends up being 1/2 cosine 20 minus I sine 20. So those should be your answers for your DIY. Now that's the end of the lesson. So work on the problems that are assigned to you and turn it in. I'm going to be checking it tomorrow.